So there's a couple of things, and take what you will. The first one is this paradigm that we've thought up through an international collaboration that we published in Nature Machine Intelligence, which is called multi-level evolution. And the idea there is that we really we try and exploit this notion of embodied cognition. So the main thing with embodied cognition at the moment is that we can now use 3D printing to create robots that previously we wouldn't be able to iterate through that many designs, right? So normally building a robot is a very labor-intensive process where a person has to solder a load of stuff together, like bolt the actuators on, and so on and so on. And that's why when people design robots, they don't typically use evolutionary processes. But now we've got 3D printing, we can have a print bed with all types of different robots on that are all designed, and that could be like one generation, right? So we print off one generation of robots, we test them all, we send it back to the algorithm which tells the printer what to print out for the next generation. So we're really on the cusp of being able to do what I would say embodied evolution properly. Now, what we're saying with multi-level evolution is that not only do we consider the shape of the robot, the controller, and how those things interact with the environment, we actually search for new materials, polymers that respond to UV light, artificial muscle type actuators, these more bio-inspired, less traditional types of robotic components. And we can set up processes, again, using evolution, to search for these different types of materials, and then we can bring them up into components. So we can select a geometry of a component and we can bring different materials into it, test it out, see how good it is. And when we get some good components, we can bring them up into a robot, test it out, see how good it is. It's a concept that we call materials to machines. So it's really being able to specialize, to tailor these bespoke robots all the way, theoretically, all the way from the molecules they are made from to the holistic behavior of the robot and its controller in the environment.
I come from a psychology background, so just hearing you talking about this makes me think that this is a wonderful way of getting out of our rote way of understanding ourselves and the environment, so schemas, and being able to have, like you said, these novel things emerge without being limited by the schemas that we have in our heads.
Yes. So, well, I mean, there's two ways of looking at it, right? And one of them is when we set these algorithms up, like I mentioned at the start, when we set them up, we need to set them up so that they succeed. And one way that we can do that is by making sure that there is like radial symmetry, bilateral symmetry, all these things that we know generate good body plans. So we can embed them in. But the really interesting thing is, we know evolution is incredibly powerful and incredibly creative, and it's certainly the paradigm we want to be following in creating robots like this kind of next generation new breed of robots, right? But when evolution works in nature, it's constrained by natural materials, cartilage, bone, flesh, muscles. These things have specific material properties, and our robots, the things that we print, the things that we can cast and mold and whatever, things that we can create, those material properties are different. So that when we apply the same process to the two things, we'll end up with robots that are evolved but look unlike anything that we have seen before because the material properties are different.